Welcome and let's begin a new session. Here is a problem at your screen, and it was referred by many since 2014. And though it's a only 3 point question, but the problem itself has earned some respect among the problem solvers. So I'm going to do it. The statement of the problem reads: a small puck. Oh, that means a small block or something of mass small m is carefully placed onto the inner surface of a hollow thin cylinder of mass capital M and radius capital R. Okay. Initially, the cylinder rests on the horizontal plane and puck is located at the height R above the plane. That means it is occupying a horizontal position right now, as shown in the figure. And unfortunately, this is not left, this is right. But in the original problem, the figure was placed on the right, on the left. So, next line it reads: find the interaction force F between the puck and the cylinder at the moment when the puck passes the lowest point of its trajectory at the bottom of the cylinder. That means this. Assume that the friction between the puck and the inner surface of the cylinder is absent, and the cylinder moves on the plane without slipping. So it's a case of pure rolling. The free fall acceleration is g. So everything is static at rest. At the start, everything is static at the start. And the advantage lies with the puck of mass small m to start any motion. And guess the condition at its disposal. It has got to slip down over the surface of a smooth cylinder, and to provide a kind of support, the cylinder will try to slip towards left in order to hold it from below. But the slipping is prevented by the static friction able to act at the point of contact with the surface beneath. So that means the friction awakes and stop its slipping by acting towards right, and as a consequence of it, it provides the friction itself provides a counterclockwise rotation to the cylinder. And the main thing is friction needs to act towards right. So we have analyzed the problem initially. Now we need to complete the free body diagram of the cylinder and the puck at a later moment. And I'm willing to draw a diagram for this. And let we have a cylinder like this, and there is a horizontal surface beneath it, and the puck position, I would like to give it a position here. Puck is somewhere here, came down, so that and this is a vertical line. So a normal force will be applied on the puck by the cylinder, and so does the puck on the cylinder. This normal is on the cylinder, and this normal is on the puck, and they are exerted by each other. And there will be a normal as well at this position on the cylinder, and Also, you can show its force of gravity acting on both the objects, a small mg on the puck and capital Mg on the cylinder. And well, it needs some explanation now. Let this angle is equal to alpha at this moment. And thinking of this moment, or at the moment when the puck reaches to the bottom of the cylinder, let's suppose that it has a velocity u towards right, the puck at the bottom, and just consider it has got some velocity v towards right, and at the same time the cylinder has got velocity v, and it is of course towards left, such that the velocity of the puck with respect to the cylinder is horizontal, and this will be equal to u plus b, of course. And now consider an observer sitting at the center of the cylinder, and this observer will have an acceleration along the horizontal, but no acceleration along the vertical at all. So discarding any pseudo forces acting on the puck in this frame in horizontal direction, it can be said that it is only subjected to real forces, that means the force of gravity and the reaction force, that is obviously the normal reaction force of the cylinder on it. Let's call it F, because in this question this force is considered as F, and this is the thing we need to find out. So for this observer, the cylinder is moving in a circle of radius r, and at this moment when the puck reaches to the bottom of the cylinder, its equation of motion can be written simply as F. N1 will be replaced by F at this moment, F minus mg. Puck is here, remember, and that is equal to m v relative square upon r. That is the velocity of puck with respect to the cylinder. And this is, I think, is the main plot of the solution of the problem. The physics of the problem is now completed. Rest of the things can be found based on other information provided in the problem itself. Since the velocity of the puck becomes horizontal at the bottom of the cylinder, we will need the region behind its change. So we write its equation of motion along the horizontal, because we are only interested in the velocity. Initially it was at rest, and at the moment we need to find its velocity is when it reaches to the bottom of the cylinder, where its velocity become horizontal. So we are interested in the changes in the horizontal component of its velocity. So I would like to find the regions behind changes in the horizontal component of its velocity. So we will need to write its equation of motion along horizontal direction. It is a point, so its equation of motion is going to be simply net force equals mass into acceleration. And I guess in this case the horizontal component acting on the velocity is only this component of normal along the horizontal we are interested. And since this angle is alpha, and this angle will become 90 minus alpha accordingly. So the normal component, the horizontal component of the normal reaction of the cylinder on the puck will be simply written as n sine alpha, and this n sine alpha is the mass into acceleration of horizontal component of the of the acceleration of the puck, and let's write it ax. So this is my equation number 1, and we will also need to know the horizontal component of the cylinder at this point as well. So we write equation of motion of its center of mass as well. First the center of mass, and you can see here this is the component that is acting it here, and the angles are again 90 minus alpha. So we can write the horizontal, although it has got two forces acting along the horizontal. One is this and another one is this, and its acceleration is in this direction. So I'm going to have to write something like n sine alpha minus f, that is equal to mass into acceleration of the center of mass of the cylinder, that has been taken as capital A in this case. And again, since it is rotating, we need to write the equation of motion of rotation about the axis passing through the normal to the plane of the paper and passing through its center of mass. So this axis basically is rotating in this manner. So I can write here the equation as since only the force friction is producing torque about this axis, so we need to write an equation like this: Fr is the moment of the friction force about the given axis equal to its moment of inertia multiplied by its angular acceleration. And this is the equation number 3. There are other useful equations like since the cylinder is rolling, purely rolling without slipping, so I can write acceleration of the center of the cylinder simply by A equals r beta. Beta is the angular acceleration of the cylinder, and I can also write if this I equals mr square, since a hollow sphere. And from the second equation you can say here that second equation says n sine alpha equals f plus ma, and we are going to manipulate or rewrite the right hand side of this equation, or we are willing to find the value of f plus ma, and you can see here f can be written as I beta upon r, and ma as well. And next step, I would like to write the value of I, that is mr square. Beta equals a upon r, so that then another r adds it and it becomes r square in the denominator. So the final result we will get is 2ma. So we have one equation, that is n sine alpha equals twice ma, and we already have equation 1 indicating n sine alpha equal to max. So we need to equate both n sine alpha values, and we could write here max equal to twice ma from these two equations. And if you would like to write m into u, the velocity at the moment when the puck reaches to the bottom of the cylinder, its velocity becomes u. So we can write here This Ax can be written simply as dx upon dt, or dv upon dt, simply x comp dvx upon dt, and a can be written as simply dv upon dt. That is the velocity of the cylinder at any moment. And so we have got m dvx equal to 2 m dv, and integrating it from 0 to v and this from 0 to u, we get the relation something like mu equals twice mv. This is one of the equations we will be needing, because what we got is a relation between u and v, not u and v explicitly, but we simply got a relation between u and v. So to get the final solution, we need one more relation between u and v, and this can be found implying mechanical energy conservation principle, which is also applicable here. And since initial energy was only potential energy, everything was sitting here and everything was at rest. So initial energy is completely potential, and in reference to this surface, I can write the initial potential energy simply as mgr, and at the latter moment the potential energy is vanished. So because the puck reaches to its bottom and there is no change in potential energy of a rolling cylinder, so we don't need to worry about, because initial moment or final moment is its potential energy is same. So that is of course capital mgr, and so we don't need to mention the potential energy of the cylinder. There is only change in potential energy of the puck, and it is mgr, and it will be equal to the potential energy gained by all the entities like puck and cylinder. And potential energy equation you would like to write for puck, it is half mu square, and for cylinder it is half mv square plus half I omega square. And of course omega and v are related by the equation v equals omega r, because it is purely rolling. And using these two equations, you will be able to get the value of u, and that you will find is something like under root mgr plus 2m plus m, and v as m by m under root mgr by 2m plus small m. And accordingly with the relation, with this relation, f minus mg equals mv square by mv relative square by r. We have f equals mg plus mv relative is u plus v. V relative is u plus b, so it make it a square here and divided by r, and you are going to get the value of f equal to 3 mg. It is already calculated everything, so I don't need to calculate them. You can just calculate and match your result with the given result, and the answer you will get is 3 mg 1 plus m by 3m, and that's the solution. What was interesting in this question is velocities were continuously changing, and no direct relation between velocity of puck and velocity of cylinder was provided. So we have to find out by rather an unconventional way. So we did it. This was the method displayed in the solution of this problem as well. Thank you very much for watching.